All right, guys, welcome to section 3.4. We're going to be looking at the chain rule today. So another way to differentiate functions. Okay, so what the chain rule deals with is composite functions. So how do we take the derivative of composite functions? And just as a refresher, a composite function, or the composition of functions, is when we have like an inside and an outside function. So the notation we use in algebra looks like this with the open circle, f of g of x, and it's really f of g of x. So we're plugging g into the function. And I like to think of this as inside function versus the outside function. It makes everything a little bit easier to keep track of. All right, so let's practice just that part, identifying composite functions and identifying the inside part and the outside part. All right, so let's consider the following. All right, so let's say we have f of x, and I'm using capital F because it's a composite function, and we're looking at x squared plus 1 all cubed. Okay, and so my question is, what's the outside function and what's the inside function? All right, well, the outside function is we're taking something and we're cubing it. So that's going to be our outside function. So I would call the outside function f, and it's something cubed. And then what's the inside function? Well, it's this part right here. That's what we're plugging into our function. So I would call the inside function g of x, and it's equal to x squared plus 1. Okay, and then this is something that we've done in algebra. So this isn't new material, but what is going to be new is this notation that's going to help us with the derivative. So rather than saying, inside function and outside function using f and g, what we're going to do is let's take this whole expression and introduce a new variable. Let's introduce the variable u. So we can say the outside function is u cubed, and then u is a function of x, where u equals x squared plus 1. So it's the same thing that we did before, but it's just a different way of looking at it. And writing it like this in terms of u, that's going to help us with differentiation. All right, let's practice one more time. Maybe you guys can do this one on your own. Suppose we have a function, we'll call it f, and we're looking at e to the 2x. And I want you guys to figure out the inside function and the outside function. Okay, so the outside function is e to the x, equals e to the x. And then the inside function, g, is what's in that exponent, 2x. All right, alternatively, we could also write f of x in terms of u. So now we're looking at e to the u, where that exponent u is a function of x. U of x is equal to 2x. So you can write it like that too. Okay, so how are we going to take the derivative of these types of functions? Well, we take the derivative using something called the chain rule. So let's explore that. So the chain rule. The chain rule we use to find the derivative of a composition of functions. So if f is differentiable at x, oops, I already made a mistake. Sorry, guys. Let's erase that f. it's if g, the inside function, is differentiable at x, and then we plug x into g. I'll go up here. We plug x into g like this. We plug x into the g, and then g we plug into the exponent. We plug x into g, and then we plug g into f. So that's why we have that. So g is differentiable at x, and then f is differentiable at g of x. Then the composite function and I'll use capital F for that. So we can notate it like this, F open circle G, or if you don't want to get heavy on the notation, you can write out in terms of inside and outside functions. All right, then that function is differentiable at x. And the derivative is the following. F prime of x is equal to, and how we're going to do it is we're going to take the derivative of the outside function first, with the inside function still inside, and then we're going to multiply it by the derivative of our inside function. All right, and that's the chain rule. We can also state the chain rule using Leibniz notation and writing everything out in terms of u. So let's see what that would look like. I'll write it in a different color. So in that case, I'm going to switch over to y's. So dy dx, the derivative of y with respect to x, we would take the derivative of the function, derivative of the outside function with respect to u, and then the derivative of the inside function with respect to x. All right, and we'll see some examples using both definitions. Okay. So here we go. So let's look at some examples taking the derivative. So let's say we have a function f equal to x squared plus 1 all cubed. And we want to find the derivative. Okay? So the derivative, first of all, why do we know we would use a chain rule? Well, we'd use a chain rule because there's two things going on, right? First, we take x. First, we take x and square and add 1. That's like one rule, one function. And then whatever that is, we're going to cube it. Okay, so this x squared plus 1 is our inside function, and then the cube is the outside function. So that's telling us that we have to use the chain rule. So according to the chain rule, we take derivative of the outside function with the inside function still hanging out inside, and then multiply it by the derivative of the inside function. Okay, so in our case, the outside function is what? That's when we cube things. And then the inside function is that x squared plus 1. Okay, so let's see what that looks like. I like to highlight just to really help what's going on. That's the derivative we're going to take first. So if we're going to take that derivative, because that's our outside function. So what's the derivative of x cubed? We know we bring down the exponent and subtract 1. So 3x squared, right? So what that's going to look like over here is we're going to bring down our exponent and then subtract 1 for the new exponent. Okay? So we know that. But then our formula is telling us that g of x, the inside function, is still inside. So x squared plus 1. Okay, so that's the first part. And now we're going to take the derivative of our inside function, x squared plus 1. So what is the derivative of x squared plus 1? Well, this is a power rule again, so bring down the exponent and subtract 1. And what's the derivative of a constant? It's just 0. Okay, so there you go. So 3 times x squared plus 1 squared times 2x. So that's the derivative. Let's clean this up a little bit. We can put this in front, right? So we're looking at 3 times 2x. I'll write it out. You don't have, you can skip this step definitely. But we're looking at 3 times 2 is 6. 6x times x squared plus 1 squared. And then that's the derivative of f prime of x. Okay, so there you go. That's one way of doing that derivative. Let's look at it in terms of u. So let's bring back that same example, but using that other definition with the u's and Leibniz notation. Okay, so in this case, u is the inside function. So let's let u equal the inside function. And then y will be the outside function in terms of u. Okay, so something like that. So now our definition says the following, that f prime of x, the derivative of that function, first we take the derivative of y with respect to u, derivative of the outside function. Then we take the derivative of the inside function, so the derivative of u with respect to x. Okay, so here we go. So what's the derivative of y with respect to u? That's just our power rule. So 3u squared. All right, and then this u, take the derivative with respect to x. So again, 2x plus 0, or just 2x. So I'm just going to rearrange a little bit. 3 times 2 is 6. U squared times x. Okay, but let's look back at our original problem. Do we see any u's here? We don't. So it's weird to have our answer with a u. That doesn't make a lot of sense. So let's go back and do a little substitution. We know that u is equal to x squared plus 1. So we're going to want to make that substitution right there. All right, so substituting u back as x squared plus 1, now this answer makes a little bit more sense. We started with x's, we should end with x's. All right, and again, we just clean it up a little bit. Let's move that x to the front. All right, and we get the same answer as before. It's just a different way of looking at it. All right, so again, whatever way you feel comfortable. Either you just dive right in and you start doing the derivative of the outside function, and then you take the derivative of the inside function, or you bring in a u as kind of like a placeholder. All right, good, guys. Let's look at another example. So let's say we had a function, and we started with this one at the beginning as one of our examples, and we said that y is equal to e to the 2x. All right, and then let's say we wanted to take the derivative of that. So let's say we wanted to take the derivative of e to the 2x. Okay, so we would first have to realize that this is a composite function. We'd have to see that there's two things happening. So one way is we would look at this and we say we plug in the x and we multiply it by 2. That's the first function. And then we do e to whatever that number is. So we see that there's two functions, two rules happening. One is the exponent, and then the second rule is e to that exponent. So this is telling us to use the chain rule. There's an inside function and an outside function. Okay, so again, we have our outside function and we have our inside function. And the chain rule tells us that we can take the derivative of the outside function first. Well, what is the derivative of the outside function? It's just e to the x, right? But with the chain rule, we keep the inside function there. So e to the 2x. And then we multiply by the derivative of the inside function. What's the derivative of g? 2. So it's 2e to the 2x. All right, and again, we don't have to do both methods, but some people, it's easier to see with a u placeholder. So we could think of this as e to the u, where u is 2x. And then when we're talking about y prime, we're going to take the derivative of y with respect to u, and then take the derivative of u with respect to x. Okay, so let's do it. So y, take the derivative of y with respect to u. What's the derivative of e to the u? It is e to the u. And what's the derivative du dx? Well, the derivative of 2x is 2. Okay, so again, we started with x's. It's weird to give back u's. So let's make that substitution. We know that u is 2x. And we see that we have the same solution as before. It's just a different way of looking at it. All right, good. So let's look at another example. We'll introduce some of our trig functions that we just learned. So let's suppose we're going to differentiate. That's what all of these instructions would be, differentiate. And let's suppose, don't do that, that y is equal to cosine of x squared. Okay, so again, we have to realize that this is a composite function, right? And we see that we have our outside function cosine and the inside function is x squared. Okay, so let's do our u. Let's write everything in terms of u. So we can think of this as cosine of u, where u is x squared. Okay, so if we wanted to find the derivative then, if we wanted to differentiate, we know it's dy du times du dx. Okay, so let's use our functions up here. So what's the derivative of cosine of u? Good, it's negative sine u. That's one of our derivatives we're supposed to memorize. And what's the derivative of u with respect to x? 2x. Okay? And let's see where we started from. We started with x's, so we have to end with x's. And we see that u is equal to x squared. So let's make that substitution. And I'll rearrange some terms too. I'm going to put the 2x in front of the sign. Okay, and then there's our derivative using the chain rule and our trigonometric derivatives. Okay, so let me compare that because there's a different way of solving it, right? We can just go for it, not using u's. And if we were to just go for it and find our derivative, we would first take the derivative of cosine, which is negative sine, but we would keep the inside function. And then we would multiply it by the derivative of the inside function. Okay, so once we get more comfortable with the chain rule, this is the steps we might take. And we can see that it is a little bit more efficient. So there's definitely some benefits to having that skill where we can just jump in and start taking the derivative. Okay, so let's do another example and then you guys can try some on your own. Let's take a look at another function, a little bit different. Instead of cosine of x squared, let's have it be cosine squared of x. Cosine squared of x, and we're going to differentiate, we're going to find y prime. All right, and a common mistake is to forget that cosine squared of x is really just telling us to square cosine. Just a shorthand way of writing this cosine x all squared. When we write it like that, we can see that it's actually a function composition, right? What's the outside function? It's squaring something. There's your outside function right there. And then your inside function is that cosine of x. All right, so if we wanted to find y prime, let's practice just hopping right in. We would take the derivative of the outside function, so bring down the 2, and then subtract 1 for the new exponent. With the chain rule, the inside function stays the same. And then we take the derivative of the inside function. So something like this, okay? Let's rearrange some stuff. I'm going to just bring, this is a negative sign, so I'm just going to bring it to the front. So negative 2 cosine x sine x. Okay, and I'm fine with this solution. This solution is dandy with me, but we'll see, with our solutions dealing with trigonometric problems and functions, there's a whole bunch of identities that we can use, right? And this identity to me looks really familiar. Sometimes we see it with the sign in front. Remember, we can rearrange factors. That's allowed. 2 sine x cosine x is our double angle formula. So we could write it as a double angle as well. But again, if you don't make that connection during a quiz or an exam, that's okay. I won't penalize you. But while we're at it and talking about it, it might be nice to kind of remind ourselves of all of the different, or not all of them because there's quite a lot, but some of them, at least the double angle ones. Remember sine of 2x, that's the one we just did, is 2 sine x cosine x. And then cosine of 2x is cosine squared minus sine squared. Okay, and that's a little thought bubble. So we'll put that in our thought bubble. Okay, so something that might come up. All right, guys, let's have you all do some of these differential problems. So let me write them out, and the instructions would be like differentiate, find the derivative, something like that. And I'll give you 2, and then pause it and see if you can work out your solutions. All right, so go ahead and push pause and then come back to check your work. All right, let's see how y'all did. So solutions, number 1. So I would clean this up a little bit. I like to see things in terms of exponents, not cube roots or nth roots, anything like that. And also, there's only a cube root on the denominator, so I can actually rewrite that expression with no denominator. Right? I can do that with a negative exponent. So that's what I'm going to do. I'm going to start there. Okay. Otherwise, we have to use the quotient rule, and our problem just got a lot harder. All right. So we could still do it without writing a negative exponent, but then we'd have to use our quotient rule. So this way, it's a little bit more direct. Okay. So once we do this, it's a little bit more straightforward. So the derivative, we see we have 2 functions. We have a power function, and then we have the inside function x squared minus 1. So to take the derivative, let's do the power function first, bring down the exponent, and then subtract 1 from the new exponent. The inside function stays the same. And then we multiply by the derivative of our inside function, which is 2x. Okay? Okay, so let's clean it up. All right, so lots of things at play. I see we have a denominator of 3. So I'm probably going to write everything in a fraction. Because look, we definitely have a negative exponent. We're not supposed to have negative exponents in our answers. Sometimes it's okay, but sometimes it's also kind of fun to see how far we can simplify something. So we have a negative sign. And what's in the numerator? Let's see, we have a 1. This whole thing will go to the denominator. Looks like only 2x is hanging out upstairs. Downstairs we have a 3. And then we have an x squared minus 1. And now our exponent is positive. Something like that. We could leave it like this. We can also simplify this and use our root notation, since that's where we started. And if we see this, we have a whole x squared minus 1, right? Because 4 1/3 is like 1 1/3. I'll write off that off the side. So 4/3 is like 1 and 1/3. So we have an entire x squared minus 1. So we don't need a root function around that. But then we do have a cubed root of x squared minus 1 left over. All right, and that goes back to simplifying radical expressions, if you guys remember that, going back to simplifying radical expressions. A little bit of algebra side work for that, if anyone is interested. And we always are, because algebra is so much fun. So I just said 4/3, look, it's like 1 plus 1/3. That's this work over here. So when we add up exponents, that's like multiplying with the same base. Right? 1 plus 1/3. So just going backwards. And then from this step, that's going right here. Okay? So there you go. So there's our derivative. A lot of simplifying in that one. Okay. So let's see how we did with number 2. Number 2. That one's involved, right? We have not only a composite function, we have 2 composite functions, and we're multiplying them. Okay? So we're not allowed to just come in and start doing the chain rule, right? Because the chain rule is only for a composite function. This is a product of composite functions. So that's not what our chain rule tells us. So what we have to do before that is we have to use our product rule. So we can call this f, Oh, g's already taken, so I'll use h for that. And now g of x, excuse me, the derivative of g of x, we're going to use our product rule first. All right, so something like this. Okay, so f of x times h prime of x plus h times the derivative of f. All right, so here we go. So f of x is x squared plus 1 cubed. Okay, here's h. What's the derivative of h? I'll use a different color. Well, this is a composite function. So let's take the derivative of the outside function first. All right, there's our power rule. Inside function stays the same. And then we take the derivative of our inside function, which is going to be 2x. Okay, so that takes care of this part. Now let's keep going. And then we're going to add h of x. And then we're going to take the derivative of f prime, this first function. And again, it's the outside function is the exponential function, excuse me, the power function. And then the inside function is x squared plus 1. So we'll take the derivative of our outside function first. Inside stays the same. And then we'll multiply by the derivative of our inside function. Okay. Whew. And that's that. So it's time to start cleaning this up. So let's see how we're going to do it. So in this first one, so this is all one term, right? It's all multiplication. So I'm going to multiply, I'm going to put the constant in front. So I have 6 times a 2x. I'm going to move that to the front. 6 times 2x is 12x. And then I have an x squared plus 1 cubed. And I have an x squared plus 2 to the 5th. All right, and that's that first one. And again, this second term, this is all multiplication, so I can rearrange the factors. So what am I going to do? I'm going to do 3 times 2x, and then I have a x squared plus 2 to the 6th, and then I have a x squared plus 1 squared. Okay, something like that. And again, I'm fine. I like a little simplification. I like the products to be in the front of, excuse me, the constants be in the front of the term. I like the coefficients be multiplied, stuff like that. So I think this is a great simplification. Sometimes our textbook, or sometimes we might want to take it a step farther. And if we wanted to do that, we could factor out a common factor, okay? The greatest common factor. So for instance, if we start with the coefficient, 6 is the greatest common factor. Then we have a factor of x in common. And x squared plus 1 is in common in both. And we have, let's see, take the lesser exponent. We have 2 copies of x squared plus 1 in each term. And then we have an x squared plus 2. What's the lowest exponent? 5. So we're going to be able to factor out an x squared plus 2 to the 5th. All right, so that big ginormous thing is our greatest common factor. Okay, pretty epic, right? Let's see what's left over. So we took out a 6x, so factoring out is like dividing. So we'll be left with the 2. Here we took out x squared plus 1 squared, but we started with 3. So we still have an x squared plus 1 left over. And then we took out an x squared plus 2 to the 5th. So we took out that whole thing, okay? Next, 6x, we took out a 6x. x squared plus 2 to the 6th. Oh, we only took out 5 copies, so we'll be left over with 1. And then we took out x squared plus 1 all squared. Okay, whew. We can clean this up, distribute the 2, combine like terms. And then we have this ginormous thing. So this is also a solution if we wanted to. And notice this solution is completely factored, which is always nice. So this is also the derivative. It just looks a little bit different. Okay, so let's end here for part 1, and then part 2 we're going to start by talking about exponential functions.